morning, everyone. I am so excited to be here together in this room. So welcome to all of you. Welcome to those of us joining us virtually. We actually sold out in person today, and then we had a huge response for online. So I'm excited for us to be together and have some really great conversations. So as you know, the pace of change in technology has been staggering. And 2025 is shaping up to be a really defining year. AI is reshaping every corner of the economy, from healthcare to transportation to media. And the question all of us are wrestling with, whether we're a technology company or we are a technology company, even though that's not our main thing, is no longer what technology can do, but rather how can we harness and use technology responsibly, creatively, and equitably. And so today's summit is asking bold questions, sharing real solutions, and challenging assumptions. You're going to hear from founders, from engineers, researchers, journalists, investors, and community leaders, all pushing the boundaries of what's possible. And we are very excited to also celebrate our 2025 Tech Power Players and end the day with a startup pitch contest and a conversation with Massachusetts Governor Maura Healey. We hope you're going to leave today inspired, informed, and energized, and we're just really grateful to all of you for being part of these conversations. I didn't introduce myself. My name is Linda Henry. I serve as the CEO of Boston Globe Media, and we are starting things off with a bang, as we have a terrific thought leader, entrepreneur, and overall Renaissance man who's leading and helping us define a new Renaissance now, founder and CEO of Flagship Pioneering and co-founder and chairman of Moderna, Noubar Afeyan. Noubar, if you could walk up and join me. So Noubar has dedicated his career to improving the human condition by systematically creating science-based innovations that serve as the foundation of startup companies. I love the way that you define what you do. You can come grab a seat on the couch while I brag about you a little bit more. Noubar was born in Beirut to Armenian parents and did his undergraduate work at McGill University in Montreal, and he completed his PhD in biochemical engineering at MIT, and now, amongst many other things that he does, he serves as a member of the corporation at MIT. So we're excited to talk today. Thank you. Welcome. Of having conversations with Noubar before, and I have to say, they're one of the places where I've seen people take the most notes on what you say, and because Noubar is very much a thought leader in this, and he writes the most incredible annual letter, and his 2025 annual letter starts with a beautiful quote from Leonardo da Vinci.
And by looking at who's been there before, it's quite remarkable just how much clearly Leonardo da Vinci, without necessarily the measurement tools, without the knowledge that we have today, instinctively had this sense about the hidden order of nature, and he was guided in much of what he did by almost, I'd say, an obsessive curiosity about how nature did what it did. And I think that he had figured out that there are laws in nature, there are designs, there are repeatable patterns that if you could only tap into and discern, could lead to lots of inventions. And I think more than really anybody else, he epitomizes, I think, the age that we're going to get into, where if he was alive, the tools that are now available would actually realize much of what he envisioned. And it's remarkable how much he did with what little he had to work with, and he invented a lot of his tools. But I think it's really important, I think, to credit him with being one of the first to think about this notion of what we call polyintelligence, which of course many people call him a polymath. And the root of the word is similar in the sense that if you integrate all types of knowledge, you find things that are quite different than if you just look at it from one prism.
So this polyintelligence, which did you coin that phrase?
We certainly proposed it.
You proposed the
I don't
word
know if
polyintelligence.
History will tell whether we coined it, but we certainly proposed it.
Well, the concept of it, which is sort of founded in this renaissance and this combination, can you talk about how that would apply to companies?
So let me first describe for the audience, I assume most of you will not have seen the letter, but what it is we're talking about. So, you know, we all grew up in society generally kind of recognizes one form of intelligence, which is human intelligence. And we, you know, humans are filled with the humility and the hubris of thinking they're the only intelligent beings on basically that's known. And we understand one form of intelligence, the one that we have. And it's taken, I would say, a human creation of a machine that is increasingly acting in seemingly intelligent ways, and I say seemingly very carefully, something that didn't happen overnight. It's been a field that actually much of the roots of it are in Massachusetts. But it took a human-created machine, like an airplane, but in this case, artificial intelligence machine, to actually make us realize that there is another form of intelligence that we could begin to treat that way. Now, a lot of things are said about artificial intelligence, but I think not what I'm going to say. And I will propose to you that a good way to think about artificial intelligence, AI, is alien intelligence. So if you think, well, why alien intelligence? I looked up the word alien. Alien has got nothing to do with, you know, UFOs and other planets. It's a word that's been around a long time. It just means other. So aliens were other citizens, people from other villages. The notion of alien intelligence, I do think this is really an other intelligence. Now you might say, what does this have to do with polyintelligence? I get AI, I get human intelligence. What we began to realize, and when I say we, you know, my firm Flagship Pioneering works in many, many aspects of trying to understand disease, trying to understand how plants do what they do, viruses do what they do. And we began to realize that now that we've made room for machine intelligence in our vocabulary, then why not also think about all of life, living systems, as a form of intelligence, which is not what science, biology, has really thought of. You know, we think about DNA as some storage of information, but if you think about it, the notion that a virus 5 years ago essentially took down the immune system of this planet for all practical purposes, and yet it's not intelligent? Well, guess what? If a computer virus had done that, boy, would we be thinking of it as an intelligent virus that's attacking our computer defenses. So if you start allowing yourself to think about nature as many forms of intelligences, and you, first of all, become even more humble than humans are used to being, you start realizing that the way to study it is not the base pairs or what we call mechanisms or all the things that we've been doing, but rather really as a form of intelligence. And you asked about companies, and I'll come to that, because that's just a complete reset of how we think about, like biology historically used to be you name things you observe, so you name birds and worms, and then eventually we realized there's cells and molecules, so we started naming them. Then we started explaining how some subset of them might be associated with some effect, and then we started making products, drugs and other things out of those. And I would argue to you that as 2025, we know an infinitesimal amount of actually biology that we're going to know if we start thinking of the intelligence that's embedded in it. And why do I call it intelligence? Just kind of ask yourself. So, you know, how do we store and process and use information to act, to behave in our brains, right? It's basically a process of learning, and then we start acting on that learning. So it's encoding information that we perceive, whether it's force-fed to us or it's just observed, and then it's the processing and use of it. Machines are doing that, so big data models are essentially getting fed training set data sets, and then they're developing models. Well, if you just think of DNA as just a model that is essentially grabbing information, ambient information, of what gives it advantage to survive, then all evolution is doing is essentially encoding learned information about nature into the particular organism. So I say all this to say polyintelligence for us is the juxtaposition of human, machine, and nature's intelligence. And that last part, I think, and many of the computer, or let's see, AI giants are saying this nowadays, life science, nature, and the problems, health, et cetera, are going to be the biggest beneficiaries of this, in my view. The first beneficiaries will be auto-summarizers and co-pilots and all the things we can talk about. But the ultimate beneficiaries, in my view, will be a level of understanding of life and how we function and how we can be better protected, et cetera, in terms of threats. That's what we mean. Now, companies that are essentially developing products and services that can use this, in my view, will have an altogether different advantage than if you view it the old-fashioned way. Long answer, sorry, but that's
No, not at all. So you, in your letter, you gave us a definition of intelligence, which you highlighted there, and you said intelligence is a capacity to learn and encode those learnings in ways that generate meaningful, adaptive models of the world, leading to effective decisions or actions, which is why your definition of intelligence includes nature, and includes that science. And well, why don't we get to the question of sort of, if you take that understanding of intelligence, how are your companies applying that sort of poly-intelligent approach to what they're doing?
So, I mean, I'll give you a couple of examples, and I'll build up to kind of the most recent thing we've been doing. So maybe 6, 7 years ago, we started asking, okay, so, you know, we know, for example, that much of biotechnology is about making protein drugs. And we've studied proteins kind of the way physicists study them, which is kind of a bunch of atoms and molecules that are essentially interacting, and there's a three-dimensional structure, and it's studied using quantum mechanics and how this thing is formed and folded, and there's lots of great work that's been done. But in the end, I'm saying this largely for shock value or to wake you up. In the end, all that happens is a piece of DNA is passed on to the next generation, the daughter cell, and that protein magically reappears. Now, the cell doesn't actually know theoretical physics, doesn't even know a theoretical physicist, has no idea what a protein is, an amino acid is. It just happens. So the DNA itself clearly encodes everything that needs to be known, and that you don't need to know alpha fold and folding patterns, et cetera. So it occurred to us 6, 7 years ago that if we take enough examples of proteins of a given function and the underlying DNA and teach the system nothing more than just the underlying sequence, that which we know is transmitted, and the ultimate function, could we teach models, predictive models, to make yet another version of that protein, having nothing to do with the original DNA that coded for the ones we showed? And so we started playing around with that, and it was really not scientifically rigorous because there's no reason to believe that's going to work. But it turns out that if you show 100 examples of a green fluorescent protein, or 1,000 examples, and we have a lot of these in nature, the computer system will start generating things that if you make in the lab, fully 50, 60% of them are actually green fluorescent, for reasons that we have no idea. They don't look structurally like what the green fluorescent proteins look like. They don't use any of the same physics. They just end up being that. So we started saying, okay, well, what happens? This was long before large language models existed. Can we start creating design platforms for proteins? First, making better proteins, then making completely new proteins. So for example, we published a paper not too long ago in a model called Chroma, which is really the first computational generation model in this space, where we asked the question, can we create a totally new protein that will look just like a human protein for all practical purposes? So you train a model that can tell human proteins from non-human proteins. And then you train a generator that actually proposes a sequence that is a human protein based on this model. And then you make these things, and you start comparing them to human proteins. So these are, you might say, well, what's the company doing? Well, the company has used all these learnings, this is pretty basic stuff, to generate many different drugs, the most advanced of which is entering, hopefully pretty soon, a phase 3 trial over the next few weeks in an immunology condition. It will be a fairly substantial drug, we think, computer-generated. It targets a bad protein, if you will, called TSLP. It's an antibody against that. Computer-generated, we made thousands of these using computer generation, learning cycles. So they have about a dozen different programs that they've started to develop and advance. 2 of them, one already tested in humans, which is an interesting example. All of us heard about spike protein during COVID, and this was this protein that the virus uses to get into cells. Well, it turns out that that spike protein is what mutates, and so every time that mutates, it escapes our immune system. So you might say, okay, well, why don't people make antibodies to a piece of the protein that doesn't mutate? And so we asked that question. Well, it turns out that the part of the protein that doesn't mutate is one that isn't under any pressure, which means it's not immunogenic. So if you take a protein, this top part is really immunogenic, antibodies are made, and the virus escapes. Another part doesn't really elicit immune response, so the virus doesn't really mutate. So then we said, okay, well, why don't we make an antibody to that part? Now you might sit there and go, why do I need a computer for that? I just make an antibody to that part. But notice I just told you it's not immunogenic. You can't make antibodies to that part. The sequence, the surface that's presented is not very susceptible to antibody binding. It turns out, we didn't know this. But the computer couldn't care less. And so we generated a whole lot of antibodies that bind to that part. We went into animals, then we went into humans and showed that these things bind the part of the spike that has never mutated, which means it has very broad antibody applicability. Now the bad news is that it was 2023, 2024, and the pandemic hit 3 years earlier, 2 years earlier. The good news is we now know how to make an antibody against any other virus at the part where the virus can't easily mutate. So it turns out the reason it can't mutate that part is that's the part the virus uses to insert itself into the cell. And if it mutates that, it's completely impotent. It can't get into cells. So computers will be able to help us make things that actually nature doesn't make, and that's just one example. I can give you many other examples. One of the things that people in biotechnology here may know is that today you make drugs against targets. And a cell may consist of 10,000 proteins, and it's interacting with hundreds of other proteins, but we pick one, and then we make a drug against that. Now, for those of you who are not in this field, you might think, who left that protein such that if you just hit it, suddenly you cure cancer, you cure heart disease? Like, how did that happen? You know, we know that we can turn the lights off here because somebody put a light switch. But who put the light switch in the cell? And you'd be right in asking that question. And the reality is that the reason our drugs work ever so slightly in ever so few people is because there is no light switch. We just happen to make drugs against things we deem as light switches, and they work on some extent, but not curative, right? But if the whole cell, if you think of it not as one switch, but a whole bunch of switches, then the question is, can you use computational approaches to study how cells change their state and how small molecules might cause their state to change? That's a really tough problem to do as a molecular or biochemist. Turns out the computer does a good job. So we're developing drugs, small molecule drugs with that approach. A company called Celerity generates the one I gave you an example of. And then the last thing I'll say, sorry, I'm going on and on, is that the next frontier we think is that these approaches will essentially transform how we do discovery science. And that's to me what's the most exciting next wave.
I want to dive into that. I want to mention that on the back of your program, there's a QR code, and there's one up on the screen too. So if you have a question that you want to submit, I'll see it here. So with this polyintelligent renaissance that we're in right now, how do we prepare people for this? Like, what should MIT, what should these other colleges be focused on? What is the right education in order to understand this?
That's a tricky question. So first, I think as humans, we're going to have to kind of find our way to being actually humble, as opposed to kind of feeling like we've now become super duper experts and we know almost everything there is to be known. So that, I don't know how you insert that in a place where you're trying to make these experts, but I think that's going to be important. Second, the question will be, how do the future scientists, future educated folks actually cooperate, not just coexist, with thinking machines, with which they can actually do their work, and making room for that, becoming interdependent on that. You know, I'm pretty dependent on my iPhone, so that the iPhone has actually largely hybridized into my life. Think of things that are going to basically be kind of anticipating what you're going to think next, what question you're going to ask next, or 10 steps later. And you may not want that, but you may just say, you know what, I don't want somebody figuring out what I'm going to do next. But you know, you're pretty predictable, it turns out. So most people think they're extremely unique, but if you show enough examples. So you know, one of the things I've been interested in playing around with, for example, is that you know, we're all obsessed around where our DNA comes from. Well, there's people who started doing work on faces and related faces and correlating it with DNA. And it turns out just by facial features, just like you could, once you see a cousin of yours, even distant, you'll remember your grandmother whose features are there. Well, the computer can do that in spades. And so essentially figuring out relatedness, as awkward as it may sound, these are all things that are going to be, we're going to have to make room for that level of kind of, let's say, predictive capability. I'm not answering your question about education because it's a long thing. There is this thing called artificial general intelligence, which is essentially the ability for a machine to reason and behave in a way that humans would against any given problem, such that it's indistinguishable from a human. And it's not clear when that threshold will be crossed. People are arguing whether it's 3 months from now, a year from now, 3 years from now, or ever. Assuming for a second that it's in the next 3 months to 3 years, then the question will be, what will education look like then? Because any one of us, however educated, will have access to the totality of knowledge that all experts would be able to yield in that space. Now, we all know that reasoning is not the only thing we're supposed to do. We're supposed to imagine, we're supposed to create, we're supposed to have emotions, all of which we will do. But when you have that level of reasoning, the question is, what are you learning in a classroom? And will a teacher without an AGI be able to teach a student with an AGI? So then what does a teacher with an AGI do to interact with a bunch of students with their own AGIs? And these might seem like science fiction to you, but I would say you'd be making a mistake if you think that you have the comfort of this being really futuristic, because it's not that futuristic. And some people will adapt, make mistakes, kind of probably suffer along the way. I don't mean job-wise, I mean just making a lot of, foolish mistakes. But at some point out the other end might come capabilities that are quite superior and competitive. And so we're going to have to, education establishments like there are in Boston, MIT, others that I can at least see, are just beginning to experiment with that. It's very tricky for education because education is rightly a super conservative activity. And nobody wants people to experiment on your kids. It's okay if they experiment on other people's kids, but not on your kids. Well, how are they supposed to experiment then, right? Because nobody wants their kids experimented on. So you get education being very, very reluctant to change. And this is kind of a sea change that I think is upon us. So it's going to be interesting to watch.
Really interesting. You talked about, there all the industries are being disrupted, and you were upstairs. You were talking about the game of chess, and how the game of chess has been transformed because of computers and sort of these other activities that we relied on are what you called our conceit in our own intelligence, and how offloading that to computers, offloading some of those to computers, and where should we be focusing? If those are, is it more that you see that it's instead of competing or picking different lanes that we find new ways to collaborate? Is that your?
Yeah, it's a great question because we can talk a long time. Focusing is an entirely human thing too, right? Because we work on a few. First of all of us think that we multiplex. I think you guys may already be aware. There's been pretty definitive studies done saying there is no such thing. You cannot actually multiplex two intellectual activities at the same time. That's at least the more recent papers. So I think we're very much focus-oriented because we're sequential machines, right? If you have, so I give an example. In the near future, if you're a scientist, even if you know nothing about a space, you can essentially, based on all published literature, generate hypotheses of a quality that's pretty similar to the experts in that area, except you can generate 1,000 of them. So if you can generate 1,000 hypotheses, not sequentially the way we do as scientists, but in parallel, and actually select from among them the ones that are the most easily testable, the ones that have the most distance from the present publications, all of which you could kind of quantify. Focus is going to be an interesting thing. Do you rather do more things with the same resources, or do you get further by doing one thing? And I want to just pick up on the chess thing because we're going to run out of time. I want to at least have the room think about it the way I was kind of hit with it early in the year. Turns out that one of the grand chess masters is somebody that I've gotten to know, and I'd never really asked him this question. So earlier this year, his name is Levon Aharonyan. He's one of the top 5 in the world. And I said to him, how do you actually learn how to get better? And his basic answer, I'm not paraphrasing, is he said, basically it's really hard for humans to get better by playing humans anymore. You have to play computers. And I kind of thought, okay, well, why is that? And so his explanation, in a way, was pretty shocking. I had not understood this. All of us have heard about DeepMind and the Google kind of Go and chess kind of machine learning approaches. The thing is, in a nutshell, it's this, just to think about this and port it to science. I'm not going to give you the actual numbers because I don't remember them. But let's just say that humans have forever only ever played 500,000 chess games. I may be off by a digit. I'm not. It doesn't really matter. 500,000 chess games, right? All humans. So all the most expert chess kind of gurus are teaching their students is the benefit of that, right? Now, when machines started playing machines, which was the big step jump, these machines played 100 million games. And so if you said, okay, if these machines didn't exist, when would humans have played 100 million games? Well, we can estimate 50 years from now, 500 years from now. I don't know what the number is. But in any case, no time soon. And the coaches of that time are now able to coach through machines coaching the chess players of this time. So now you might be saying, well, are we going to saturate this? So the interesting question is, how many chess games can be played? Turns out some people had the time to calculate that. And the answer is 10 to the 120th. There's 10 to the 120th, I'm told, it's online, you could look it up through AI, games that can be played. So you might now say, well, wait a minute, this is all garbage. Because whether you play 500,000 games or 500 million games, out of 10 to the 120, who cares? And it turns out the answer is, since it's a game where you're playing one against the other, you don't have to know what 10 to the 120th would have taught you. But if you know what 500 million would have taught you, you can beat the 500,000 version any day. The same, I believe, will apply to science. If scientific experiments are done at a rate in parallel that are 1,000 years of human scientific experiments at some point, and that knowledge is brought to bear on the solutions we're looking for the planet, for food security, for energy, that is a world that we already have manifest in chess, in Go, etc. Now, it's not a one-to-one kind of correspondence because we think science is really different, but science takes imagination, science takes strategy, science takes a lot of uncertainty. You don't actually know what the other side's going to do back. So I would urge people to think about this as a technology that is going to be more akin to human activity and more impactful than anything we've seen.
I want to just close with one final question. And you just referenced that your science relies on imagination. And I think that that's one of the ethos of Flagship that you goes to all of the companies that you start of this question of what if. And so, and it seems like it's one of the things that's sort of preparing you for this renaissance, for this revolution that you're in now. So if you could talk a little bit about this philosophy.
So, when we do discovery science or science in general, we're taught to explore the next logical extension of whatever area we're in. There may be many adjacencies, and so we're meant to create hypotheses of a given distance from the present. If you went to the NIH, well, unfortunately now you probably wouldn't get very far, but if you went to the NIH and you said, I want to work on something that's a far cry from what's already proven, you couldn't get money for that because there's no reason to believe it's going to work. So if you think about what peer review is, if you think about what publications ensure, I would argue they enforce a intellectual gravity on what hypotheses you're able to work on. That makes sense because everything builds on everything else. But we know today that something we're working on today, if somebody had proposed it 15 years ago, would have been rejected, but a subset of them actually turned out to be true. This is what we learned with mRNA. When we started in 2010, we asked the question, what if you could stick a molecule in the body and make any protein you want? You could not get academic funding for that because people would say, how are you going to do that? And we didn't have a way. We just thought first, like, okay, but if you could do that, what would result? So what I just described to you is the use of a faculty I would argue humans have that we underuse, which is imagination. We are all creative people. Everybody here is creative. And so we use that. But we don't use that to make big leaps in our scientific engineering endeavors because you're supposed to use it in art and in other areas, but not in science. Leaping imagination is kind of cold, right? Because people don't take you seriously. So what we believed is that by allowing people to ask what-if questions, finding made-up destinations initially that if you could only get there from here would be valuable. What that then does is allows you to pick a few of these and work backwards and say, okay, if I could get there, how would I have gotten there? Like, what do I have to believe 1 step before I got there, 5 steps before, all the way back to today? And that's how we practice science. The reason that's relevant for this discussion is that these polyintelligence, or at least the AI-enabled scientific approaches, are going to make this possible in a way that we could never imagine before. We used to do it through the 200 people we have at Flagship who practice this the human way, and now we're going to be able to do it, times some multiple, and that's going to be a very interesting thing. But I do think that how we can, and by the way, many people in the room might think that these AI LLMs can't imagine. I mean, how many of you think that these machines can imagine?
Beyond hallucinate.
Barely, okay, you just gave the answer. That is what hallucinating is. So if you can make errors, variation, if you can apply selection pressure and you iterate, you get novelty. If that didn't work, variation, selection, and iteration, we wouldn't exist, because that's what evolution is. And evolution of thought essentially requires variation. If you tell these machines to give you 10 made-up things, try it. They'll give you 10 made-up things in an instant. It's easier to do that than to give you the factual thing. And if you then have an agent filter that starts picking on what you think has some superiority, some advantage, one of the advantages might be truth. So you might compare it to what's true. And then, so I would say imagination is going to be enhanced by generative AI every bit as much as reasoning is. And when that does, I haven't said anything to you about emotion and sentience and all sorts of stuff, consciousness, which we can talk about another time. I'm really happy I'm going to leave. But I do think that elements, I think we will always think that these things will not be able to do a whole bunch of things that we'd rather believe we uniquely do. And while I can't tell you it'll be able to do everything, it'll do a lot more than what most of us think. That's what I believe.
Great. Well, thank you so much for your time, for your insight, for positioning this polyintelligent renaissance that we're in, and for underlining the importance of imagination and and how we approach it. So thank you so much.
Thank you. Thank you all.